Okay, so welcome everyone to this month's installment of the Working Group on Active B Stars online seminar series. Today it's my pleasure to introduce Thomas Gaudin. I'm sorry, I should have asked you beforehand. Um, Thomas is a third-year PhD student at Penn State University, working with Dr. Jamie Kenny. And Thomas is also a member of the Swift Observatory Science Operations team, working as a science planner for the mission. So today, Thomas is going to be telling us about an S-cube perspective on the white dwarf binaries as rare soft X-ray transients. And with that said, please take it away, Thomas.
All right, thank you so much for having me. Hello, everyone. Again, my name is Thomas. I am a graduate student at Penn State, and I am excited to share the work that the S-Cube collaboration, the Swift Observatory group has been doing, myself and my collaborators, over the past couple of years to explore the X-ray properties of a specific type of BE X-ray binary called BE white dwarfs. Um, as we get started today, I just wanted to quickly just make sure we're all on the same page with the definition of a BE X-ray binary, give sort of the standard theory before we complicate the picture and change that compact object. So the standard picture that we think of when we think of BE X-ray binary, we think of a O or B type main sequence star surrounded by a disk of circumstellar decretion material outflowing from that active B star with emission lines produced in the disk, giving this star its characteristic BE spectral type that we observe when we see these sources as optical sources on the sky. These sources are orbited in a close orbit by a compact object, which is typically a neutron star, in a moderately eccentric orbit. Eccentricities around 0.3 to 0.5, with orbital periods on the order of tens to hundreds of days. Now, as the name implies, BE X-ray binaries are bright X-ray sources with interactions between the compact object and the material in the circumstellar disk, providing the fuel for the X-ray emission in these systems. But these are not persistent X-ray sources. They are transient X-ray sources. They can spend years in sort of a quiescent state with low-level X-ray luminosity that's only on the order of 10 to the 34 or 10 to the 35 ergs per second, which is at or below the detection threshold for most X-ray telescopes. But after years of quiescence, these systems can produce one of two different types of luminous X-ray outbursts that we can observe due to interactions between that neutron star and circumstellar disk material. The first type, the less luminous, more frequent type, is the type 1 X-ray outburst that can reach luminosities of 10 to the 36 or 10 to the 37 ergs per second. These outbursts only last for a few days, and they reoccur typically in an orbital period timescales. Additionally, with no obvious recurrence rate, we can get these extra luminous type 2 outbursts that reach luminosities much greater than 10 to the 37 ergs per second, can even reach super Eddington luminosities. These are outbursts that last much longer than the orbital period of a system. Now, this is the sort of the standard picture of what we think of when we have a BE X-ray binary. But while we typically think of these systems as having neutron stars in them, well, there is nothing in binary stellar evolution theory that prevents a BE X-ray binary from forming with any type of compact object. It's possible to have a black hole BE binary, a neutron star BE binary, or a white dwarf BE binary. One of the main differences between these three types of systems is going to be their relative abundance. Now, BE black holes, they're thought to be incredibly rare. There's questions about how stable a BE black hole system would be, and there's only one slightly suspect candidate that's ever been found of this class of object. As we said, the standard picture is that these systems typically contain neutron stars. Observationally, BE neutron star systems are incredibly common. They make up half of the observed population of high mass X-ray binaries within our own galaxy, and they also make up half of the observed high mass X-ray binary population in the entire universe for all of our known HMXBs. But this last type, this is a very interesting type with a lot of work that's gone in to sort of understand the theoretical picture of these systems. It's the BE white dwarf binary. Now, if you look at the literature on stellar evolution of BE X-ray binary systems, theoretically, BE white dwarf systems should be incredibly common. Some studies put their abundance rates at 7 times the abundance rate of BE neutron star binaries within our universe. However, that doesn't necessarily match the observational picture that we see. If you were to plot a distribution of all of the BE neutron star systems we found on the sky versus the distribution of all the BE white dwarf systems on the sky, well, you get something that's a little bit surprising. We see on the right that our BE neutron star systems are pretty much everywhere. We find them all over the galactic plane. We have large populations in both the Large Magellanic Cloud and the Small Magellanic Cloud. In contrast, well, we very rarely see BE white dwarfs. There are 7 known candidate BE white dwarfs. 2 of these are found in the Large Magellanic Cloud, 5 are found in the Small Magellanic Cloud, and there are none that have ever been found within our own Milky Way galaxy. This leads us to an important question that is one we need to really understand if we're going to better our understanding of BE white dwarfs and BE X-ray binaries in general, and that is, where the heck are all of these BE white dwarf systems that we expect to see but are not finding in our universe? Well, it's possible that this is a theoretical problem, that we are missing something about the way these systems form. The BE X-ray binaries are thought to form via mass transfer from a high mass star to a lower mass star in a high mass binary star system via common envelope and Roche lobe overflow phases. Depending on how much mass that high mass star loses, you could end up with a neutron star or a white dwarf compact object. It's possible that there's something we're missing about this picture. We need to revisit how these systems are forming. It's also possible, though, that this is some sort of observational effect, that we are not there's some sort of observational property of BE white dwarfs that makes these systems just hard to detect, that the way that we detect these systems in general selects for BE neutron stars over BE white dwarf systems. And I think that this plays a very large role, and so to see if we can't sort of reveal that this sort of problem a little bit more, let's talk about the observational properties of BE white dwarfs, look at their signatures in multiple bands of the EM spectrum. This is a little cartoon that we can use to sort of illustrate the observational properties of these systems to see where it might be possible to detect them. I've got here on the left our BE star, a very large blue star surrounded by a circumstellar disk of material. On the right, we have our smaller white dwarf surrounded by a small accretion disk. We can look at these properties from the infrared all the way into the soft X-ray, peaking at about, or ending at about 2 kiloelectron volts, and all the way into the hard X-ray, going to 10 kiloelectron volts and beyond. Let's start by talking about the IR through UV properties of these systems. We can really lump these all together because, well, at these wavelengths, we have a very bright blue star surrounded by a disk of redder material, cooler material that is being heated by that nearby very bright blue star. So this biggest, most prominent source of IR through ultraviolet material in the system is going to be that BE star plus its disk. It is going to dominate the IR through UV continuum and emission lines in the system. You have very little hope of ever picking out that white dwarf or its accretion disk because of the overwhelmingly large amount of emission we're seeing from the companion star. So we can rule out the lower energy wavelengths. What about the highest energy wavelengths? We can go to the hard X-ray to try and see if we have a better chance. Unfortunately, the potential well of a white dwarf is much shallower than that of a neutron star, and so accretion, which should be the quiescent state of these systems, is not going to produce a lot of radiation. We expect quiescent emission in these systems to be a hard X-ray source, but it should be incredibly faint. It should be on the order of 10 to the 29 or 10 to the 33 ergs per second in X-ray luminosity in the hard X-ray band. So unfortunately, we can't really pick these out very well in the hard X-ray band either. This is at or below the detection threshold for almost every single X-ray telescope, excepting in very, very deep observations. So we're kind of out of luck in the IR through the ultraviolet and at higher energy X-rays. The place that we have to go, the only spot where we have a chance of detecting these systems, is at the soft X-ray band. Now, due to periods where these white dwarfs can produce stable nuclear burning on their surface, there are periods where we expect BE white dwarfs to produce bright, transient, soft X-ray outbursts where they become luminous, soft X-ray sources. Now this, if we can find a way to capture some data on one of these systems, observe one of these transient outbursts in the soft X-ray band, then, well, we have found our area where we can finally pick these sources out, where we can find them on the sky. Unfortunately, well, this does bring up one other problem, and that is extinction. Soft X-rays are much more easily extincted by dust and other column density material along the line of sight towards our sources. And so if you have a high column density of material, it's much easier for these soft X-rays to be extincted and to become too faint for us to detect them. So it's possible that due to the narrow band that we have to observe these in, the transient nature of the outbursts, and also the varying column density of material along different lines of sight to different parts of our sky, well, we're just not seeing these systems very well. Our best chance of detecting these systems is going to be to set up some sort of survey to try and detect these systems in the soft X-ray band. So if we were going to set up a soft X-ray survey to try and detect BE white dwarfs, how will we do it? First and foremost, we would need to scan a very large area of the sky. We want to make sure that we're scanning a large enough area that we actually have a chance of having some BE white dwarfs within our area that we're searching. Additionally, we don't want to miss any of these transient outbursts. We want to make sure that these sources are going to be we're observing regularly enough that we're going to be able to catch one of these outbursts when they do go off. We're not sort of missing them as they fade away below our detection threshold. Last but not least, extinction is going to be a problem. We've already said that that is a potential problem, so we're going to need a low column density of material along the line of sight to our survey area if we want to have a chance of detecting these sources without extinction becoming a problem. Last but not least, we're probably going to want to search for an area that already has a large population of high mass X-ray binaries. As we said, we expect BE white dwarfs to be more abundant than BE X-ray binaries containing neutron stars. And so, well, it makes sense to search through an area where those sources are already common. If you combine all of these factors together, there is one very obvious candidate galaxy that makes for the best place to search, and a dwarf galaxy that's not too big, not too small, with a large population of high mass X-ray binaries and a low column density along the line of sight towards this area of the sky. And that would be the Small Magellanic Cloud. The SMC, a dwarf galaxy of the Milky Way, is a very, very interesting target for soft X-ray surveys such as the one that I'm describing here. In fact, the SMC has been a target of many X-ray surveys over the years, which has done a great job of revealing the high mass X-ray binary population of this dwarf galaxy. Over the years, we have found that the SMC has a very large population of high mass X-ray binaries relative to its mass. This is due to a recent epoch of high star formation, which produced a bunch of new X-ray binaries that we can see today. Now, interestingly, the high mass X-ray binary population of the SMC is almost completely uniform. Almost every single high mass X-ray binary that we see in the SMC is a BE X-ray binary. This makes it a great place to search. It is also not too big. It's fairly easy to tile over it, so you can take frequent observations without having to dedicate an entire spacecraft mission to it. So we found our target. This is a great place to search, and we have, as we've said, many surveys have been done to reveal the high mass X-ray binary population of this dwarf galaxy. Now, the latest survey that has been done of this galaxy is the one that I have been working on since I started at Penn State, one that's been ongoing since 2016. That is the survey that is being run currently by the Swift SMC Survey, S-Cube for short. It's a survey run by the Swift Observatory team and my advisor, Dr. Jamie Kenna. Now, as I said, the S-Cube survey has been ongoing since 2016, and this survey is designed to detect outbursts from both new and existing BE X-ray binaries. Over the years, we've detected important outbursts from known BE X-ray binary systems. The most important of these is potentially the Super Eddington outburst of SMC X3 that we detected in 2017. Additionally, we have also been responsible for detecting several new BE X-ray binary systems, including the eclipsing BE X-ray binary that I found last year, SXP 182. Now, this survey is designed in such a way that we capture BE X-ray binary outbursts very efficiently. This survey runs every single week on Tuesday, tiling the entire Small Magellanic Cloud with overlapping tiles in the Swift X-ray telescope field of view. We can see on the right a picture of the tiles overlaid on the sky, making sure we have continuous X-ray coverage of the SMC. There are 149 overlapping tiles that we observe every single week with a 60-second observation, which pushes us down to an X-ray luminosity of about 10 to the 36 ergs per second, which allows us to detect even the faintest BE neutron star X-ray outbursts. This survey also observes simultaneously in the ultraviolet and the X-ray bands. In the X-ray, with Swift's X-ray telescope, we observe in the 0.3 to 10 keV band. In the UV optical telescope, we observe in the UVW1 band, which is centered at 2600 angstroms. Now, this survey is incredibly useful, and every single week we get a ton of very great data from each of these X-ray tiles, and we have an automated pipeline to process all of this data and search for new X-ray transients. An automated pipeline will search for new X-ray transients and flag up sources that are either existing, that have increased in brightness, or that are new sources that we have never detected before. Once we have detected a source of interest, we can produce two different types of X-ray data products that help us to analyze these systems. First one is going to be an X-ray light curve, as we see over here for one of our BE neutron star sources. In these X-ray light curves, a red line here would indicate that we have detected the source and give the upper and lower limits on the X-ray count rate of this source in the XRT band. A blue arrow is a time when we have not detected the source and we can just constrain the upper limit of the X-ray luminosity of the source. Now we can use these X-ray light curves to determine to analyze luminosity of the source and see how it's changing over time, monitor these systems for outbursts and track these outbursts, including to produce follow-up target opportunity observations where we can go even deeper and do an even better job of constraining the X-ray properties of these systems. Additionally, we can sum together all of our data from all S-cubed observations over the past 8 years and produce a very nice X-ray spectrum of our sources. Now, the automated pipeline that we use to analyze these systems to generate these spectra will automatically fit an absorbed power law to the spectrum of our sources within the SMC. This is what we would expect to be best fit to a BE neutron star system that is undergoing accretion. We expect them to be best fit by an absorbed power law with a photon index of about 1, indicating that hard X-rays are being produced by these sources. But occasionally, we will find a source in the S-cube's data that doesn't really match what we would typically see from a BE X-ray binary. We'll see sources that are very near to BE stars on the sky, but they do not fit well to an absorbed power law. Instead, well, they are super soft sources with all of their emission coming below 2 keV. In these rare cases, well, we have actually done a great job of detecting BE white dwarfs, even though this survey was not intended to find them. The way this survey is set up to detect these transient BE neutron star outbursts has done a great job of detecting BE white dwarfs within the Small Magellanic Cloud. To date, we have found, as part of the S-Cube survey, 3 different BE white dwarf systems, which represents 3 of the 5 systems found in the Small Magellanic Cloud and 3 of the 7 known BE white dwarfs in our universe. And these sources have been, 2 of them happened in the year 2020. They first went off, although publication of one did happen the next year because that outburst happened very late in the year, and the most recent outburst happened in just May of 2024. Instead of referring to these sources by their very long telephone number names, which can get confusing. I will refer to them by the year the paper was published on the source. So our Swift J0044 was a paper led by Malcolm Coe in 2020. Swift J0115 is a paper led by my advisor, Dr. Jamie Kenna, in 2021. And CXOU J0052 is a paper led by myself just back last summer. Let's go ahead and talk about each of these 3 sources, what we've learned from them, try and unveil some of the soft X-ray properties that we can glean from S-cubed observations of these sources. I want to go through each of these outbursts in detail, just so we can sort of see what we have found from these 3 very rare systems. Let's start by talking about Swift J0044, our 2020 outburst. Now, the smoking gun of a BE white dwarf binary is, of course, going to be its X-ray spectrum. As we said, we expect these sources to be super soft X-ray sources, and this one is no exception. We see all of the emission from this source coming from below 2 keV. We also see that it does not fit well to an absorbed power law. Instead, you have to use an absorbed thermal blackbody to produce a good fit to the data. This source does not have a very strong spectrum, although it does have a good enough spectrum for us to derive some of the parameters of the fit. Initially, when this source was first fit, we used a standard, the column density that is standard along the line of sight to the SMC of 5.9 times 10 to the 20 atoms per centimeter squared. When you fit with the SMC standard column density, the black body temperature that you get back out is about 90 plus or minus a few EV, which translates to about 1,000,000 Kelvin. However, you can improve this fit if instead of fixing that column density towards this source, you allow it to be a variable parameter of the fit. If you do that, well, you can see that the column density of material along the line of sight does actually increase for this source, suggesting that there might be an increased amount of circumstellar material around this binary. By letting this column density increase, it also cools down the source, giving us a black body temperature of 58 plus or minus a few EV. That is much cooler than the 90 keV value that we initially had, but it also is still hot enough for us to sort of confidently say that this is a white dwarf compact object within this system, that we have found a BE white dwarf binary. This is very exciting, and we can this X-ray spectrum does tell us a lot, but there's even more you can glean by looking at the light curve of this source. Oh, this source was first found by an S-cubed observation on the 22nd of January 2020. The source continued to be detected by S-cubed in several follow-up observations for the next couple of months. And in April of 2020, we finally had a strong enough spectrum that we could identify this as a supersoft source and trigger follow-up target of opportunity observations to monitor the luminosity of this system over time. Now, this source never got very bright. We have plotted here on the right the light curve of this system for the period of time when we were following this up with target of opportunity observations every few days. As we can see, the X-ray luminosity never reached above 4.1 times plus or minus VU times 10 to the 36 ergs per second. This is fairly faint for a BE X-ray binary. We remember back to our standard definition of BE X-ray binaries. This puts us in the range of the luminosity of a type 1 outburst for a BE neutron star type system. Would be a very faint outburst for a BE neutron star system. However, while it does have that luminosity characteristic of a type 1 outburst, this outburst lasted for a very long time. This was detected in Swift observations for over 120 days before it finally decayed below the luminosity threshold of Swift, where it could not detect it anymore. That would be more characteristic of a type 2 outburst in a BE neutron star system, lasting for that long at such a low luminosity. This means that we have a very, very confusing system. It has properties of both a BE neutron star type 1 and type 2 outburst. We need to go to the multi-wavelength data that we have available to us if we want to look and sort of analyze the origins of an outburst like this, try to determine what the heck is causing these sort of strange X-ray properties that we're seeing. Now, thanks to a long-standing collaboration that we have with the optical gravitational lensing experiment, we are able to produce very long-term I-band light curves of each of our sources after they're detected to go into outbursts. And this source is no exception, where we have a very nice ogle I-band light curve for this source, dating back for thousands of days before we see this source go into outburst. Now, typically in the I-band, BE X-ray binaries are incredibly variable. We see them vary by as much as 0.1, 0.2 magnitudes on order timescales of weeks or months, and by even more, up to 0.3, 0.4, 0.5 magnitudes over the course of 500 to 1,000 days. And in this source, we see what we would typically expect for a BE X-ray binary. This is a variable source on both short and long timescales. Particularly, I want to note that for about 3,000 days leading up to this outburst, we see the source going through a steady increase in brightness in the I-band magnitude. This can be interpreted if we assume that the underlying stellar spectrum of the star is not changing, that the circumstellar disk is growing over time. As the source gets brighter, it is producing more infrared light, and we're seeing this sort of signature play out in the system over time. This is supported by the ultraviolet data for the source, which is, as we said, observed every single week along with the X-ray in our S-cubed observations. As we move towards this outburst, we can see a definite increase in the ultraviolet light that is being produced by this source as we move into an outburst and through that outbursting phase. Additionally, to just looking at these light curves and seeing that we have an increasing I-band magnitude and an increasing UVW1 band magnitude, well, we can use Lom's-Gargle analysis to try and determine the periodicity, search for an orbital period in the ogle data, which we do find at 21.5 days, excuse me. When we phase fold this ogle data along a 1.5 day period, we get something incredibly interesting. We see that this that the I-band light curve is pulsed when you phase fold the data and detrend it along just a simple polynomial fit. We see a small pulse at 0.5 phase, as well as a very large pulse at phase 0 and phase 1. Clearly, there is some effect of this white dwarf on its companion BE circumstellar disk that is causing some sort of pulsed emission that we can observe regularly in each orbit. Additionally, Ogle not only produces the I-band magnitudes regularly for all of the sources in the SMC, it also produces V-band magnitudes, and you can use that to create a color magnitude diagram for the system. We can see that over that time period where the source is increasing in brightness, the 3,000 days leading up to our outburst, we have the source not only getting brighter in the I-band, but also getting redder over time. We have this sort of brighter when redder effect, which is commonly observed in BE X-ray binaries and is thought to be indicative of the growth of a circumstellar disk. When we put all these together, we see that we have an increased I-band and UVW1 band brightness. We see that the source is getting redder when the I-band magnitude is growing. We have a source with pulsed emission along a 1.5 day orbital period. Well, there's this one piece of only one conclusion that we can draw from something like this, and that is that we have a growing circumstellar disk, which is responsible for providing material for this outburst. If we have a circumstellar disk that has grown so much that it is now interacting regularly with the white dwarf, well, it's possible that we're seeing the BE white dwarf equivalent of a type 2 outburst. It is a point where the circumstellar disk has grown so much that there is so much material available for that white dwarf to accrete that it has entered a phase of stable nuclear burning that is able to sustain for a long time for multiple orbits. And while the circumstellar disk is this large, we are seeing the stable nuclear burning phase last, and we are seeing this sort of long duration quasi type 2 outburst that is produced by a BE white dwarf system. There's one last piece that I will note, and that is that we do see some structure in this BE white dwarf light curve. We see that the X-ray values do decay and rise on sort of a triple peaked structure. If you plot in gray the points where we expect the I-band magnitude to pulse, where we see one of those I-band large pulses, it matches perfectly with the points where we see less X-ray luminosity. This indicates that there is some sort of line of sight effect between us and this system where the disk is obscuring the X-ray emission from the compact object during these sort of high pulsed phases where we're seeing increased I-band emission. It seems that while we are seeing consistent X-ray luminosity from the source during its outburst, there are points where the disk is obscuring our view and we cannot see as strong of X-ray emission. This would be consistent with observations of other BE neutron star systems, as well as even some gamma ray binaries that has been observed to have similar effects. So this is an exciting source. We found a BE white dwarf binary. We see that it's going through some sort of quasi type 2 outburst where we see stable nuclear burning on the white dwarf producing soft X-ray emission. Let's talk about another outburst, which is going to have some similar properties. This is our 2021 outburst. So within a year of S-Cube detecting its first BE white dwarf system, it is able to detect a second, and it's going to be able to detect a second with an even more detailed X-ray spectrum, which gives us even more information that we can derive from the fit. Again, we see this is a super soft source. Our 2021 source does produce emission that's a little bit, that reaches higher energies, but never goes beyond 2 keV. Additionally, this source does not fit well to an absorbed power law. Instead, we again have to use an absorbed thermal blackbody model to produce a strong fit to this system. Now, the source, though, we have detailed enough information on it that we can actually improve our fit if we add some more features to this spectrum. And if we add a single absorption edge in our best fitting model, then we produce our best fit. If you use an absorbed thermal blackbody model with a single absorption edge, you get a best fitting blackbody temperature of 96.7 plus or minus a few keV. Again, a temperature of around 1,000,000 Kelvin. If the best fitting energy of this absorption edge is 0.864 keV. This is interpreted to be the signature of an oxygen 8 edge, which has been observed in other white dwarf systems. And if you fix all the best fitting values in XSpec and allow the normalization of the fit to vary, well, using the standard distance to the Small Magellanic Cloud, you can derive a radius of emission for this system. The radius of emission for this system is about 1,600 kilometers. Putting all of these parameters together, a super soft source with this blackbody temperature, this radius of emission, and signatures of an oxygen 8 edge, we can interpret this to be consistent with a 1.2 solar mass carbon oxygen white dwarf that is responsible for producing this X-ray spectrum. It is the compact object in this system. So again, we have found a smoking gun signature of a BE white dwarf binary. So the other piece of the pie is to try and examine how the system is going to change over the course of its outbursts. And again, we see a very uniquely structured light curve. Its source was first detected on an S-cubed by an S-cubed observation on the 29th of December 2020. Again, this outburst continued for many months. It was detected for over 120 days again before finally decaying below the detection threshold of Swift. Now, this source, despite producing another very long outburst, we still do not see it to reach a very large X-ray luminosity. Again, we're seeing this source reach an X-ray luminosity of 3.3 plus or minus a few times 10 to the 36 ergs per second. Again, we have this source with an X-ray luminosity consistent of a type 1 BE neutron star outburst with a duration that's more consistent of a type 2 BE neutron star outburst. Additionally, we're seeing some very interesting structure in this light curve that is worth probing in a little bit more detail. In order to learn more about the system, again, we're going to have to turn to our multi-wavelength data. Again, we have both Ogle I-band data available for the source as well as detailed ultraviolet follow-up as well. So we can look at our Ogle light curve dating back all the way to, for again, several thousand days in the lead up to this outburst. We see what we would expect, a strongly variable source on the order with variability on the order of 0.1 magnitude over just a few weeks or months, and as much as 0.4 magnitudes over the course of 1,000 days. Again, we also see this sort of trend of increasing brightness over time in the lead up to this outburst. We see that the source is going to grow in an I-band brightness by almost 0.4 magnitudes over the course of about 3,000 days before plateauing in the couple thousand days leading up to the outburst. If we examine the ultraviolet light curve during this period of plateau, we see another thing that we would expect. We see a correlation between the infrared and the ultraviolet light curves of these systems. We see, again, a plateau phase in the ultraviolet data of the source. We also have color magnitude data available for the source. We can see that we again have this redder when brighter effect, where as that I-band magnitude is increasing, we are seeing the source become redder over time before plateauing during this sort of I-band plateau phase of the system. So what can we again, we have the ability to even examine this in more detail. We can use Lomskargel analysis again to search for periodicity in the I-band data, and we do find that this source does have pulses along an orbital period timescale. We see a very strong pulse at about 0.5 phase on an orbital period timescale of about 17.4 days. How do we interpret all of this data that we're seeing for this system? Again, we have an increasing I-band brightness. We have a plateaued I-band and UVW1 band brightness. We see this redder when brighter effect again. We see pulses along this orbital period timescales. Again, we can draw a very similar conclusion for the system, that we see a source where the circumstellar disk has spent a very long time growing and sort of getting larger over time before sort of reaching a plateau phase, where it's able to provide more material to this white dwarf to increase the amount of material that's being accreted onto the surface of the white dwarf. With as much material available to it, eventually we reach the point where we could produce a quote-unquote type 2 outburst of a BE white dwarf system, a period where we can sustain stable nuclear burning on the surface of the white dwarf for a very long time, over 120 days. There are still some open questions about this light curve that cannot be answered in similar ways that we had for our 2020 event. The dotted lines on our X-ray light curve do represent points where we see pulses in the orbital period of the system in the Ogle data, and we can see that the X-ray light curve is not affected by the orbital phase of the system. There's no phase dependence of the X-ray emission in the system. It sort of leaves us with this question of where the double peak structure in this outburst comes from. If it's not coming from the circumstellar material obscuring the new white dwarf at different points along the orbit, then, well, this remains an open question for us to solve. What would cause the source to sort of grow and decay, and then grow and decay a second time as it's producing this outburst? It's possible that there are changes in the accretion rate of the system that are causing this, but this is left as an open question for follow-up outbursts whom hopefully we'll be able to observe later down the road in a system such as this one. So far, the two outbursts that we've seen have been very similar systems. We have systems that produce very similar luminosities, very similar durations to their outbursts. This third source, though, this most recent outburst, though, perhaps is the most interesting and important of the three outbursts that the S-Cube survey has detected to date. We'll start with the X-ray spectrum of this source. This, again, is the smoking gun of a BE white dwarf binary, and this is the brightest of our three outbursts, so we have the most detailed spectrum to work with for fitting. Again, this is a super soft source. We see no emission above 2 keV. Again, we also see a source that does not fit well to an absorbed power law model. Instead, again, we must use an absorbed thermal blackbody for fitting. Over this time, we have an even more detailed spectrum, so we can increase the number of features that we're including in our thermal blackbody model fit to try and glean even more information about this white dwarf. Now we have in this system a best fitting model that is actually best fit by an absorbed thermal blackbody, where we now include 2 absorption edges in the fit. When you do use this model and fit the source in XSpec, you get a best fitting blackbody temperature of 91.3 plus or minus a few EV. Again, this is going to be a blackbody temperature of around 1,000,000 Kelvin. We have our first absorption edge at 0.385 keV. We're going to interpret this as the signature of a carbon-6 absorption edge at 0.49 keV. We also see the absorption edge we saw in our 2021 outburst. Again, we see a signature of an absorption edge at 0.896 keV, which again, we're going to interpret as the signature of the oxygen 8 edge at 0.817 keV. Again, if you fit all of these, fix all these values at their best fitting parameters in XSpec, allow that normalization to vary, and use the standard distance of the SMC, well, you can derive an radius of emission for this object, and we see that the radius of emission in this source is an order of magnitude higher than what we observed in our 2021 outburst. We see this source emitting at a radius of about 11,000 kilometers. Taking all of this together, we can draw similar conclusions in this system to what we drew in our 2021 outburst, and that is that we are again seeing a spectrum that is consistent with a 1.2 solar mass carbon oxygen white dwarf that is responsible for producing this outburst. Well, this is very exciting. We have a very detailed spectrum that has given us some great information, but the X-ray light curve is really where this source shines, and really where this source sort of stands out as an oddball source. There's not as much detail in this X-ray spectrum because this source is very rare, was only detected very briefly. This source, I will note, was previously known to be a BE X-ray binary. It was first found in a 100 kilosecond Chandra survey back in 2009, where 12 counts were detected in 100,000 seconds. That was not enough to characterize this as a BE white dwarf at the time, but these 2 X-ray points are enough for us to make the characterization to call this a BE white dwarf, despite very limited X-ray data. The first detection of this source did not actually come from S-Cubed. It was first detected by the Einstein probe several hours before our detection on the 27th of May, 2024. Fortunately for us, S-Cube was scheduled to make an observation on the same day, and just 15 hours later, our 60-second observation picked up the source as it began its outburst. Now, I want to draw your attention first and foremost to the X-ray luminosity of this system, which is sort of the strangest, most defining feature of this outburst. This source was bright. It produced a maximum X-ray luminosity of 6.5 times 10 to the 38 ergs per second, which is greater than the Eddington luminosity for a 1 solar mass object. This is a super Eddington outburst that has been produced by this system. Additionally, while the source is very bright, it decayed very rapidly. As soon as the source was detected by S-Cube, we immediately started on follow-up target of opportunity observations. We produced a second observation less than 24 hours after the first, but due to the orbit of Swift, there are 9 days, about every 45 days, where the Small Magellanic Cloud is not visible to our spacecraft. It is obscured by the limb of the Earth. Unfortunately, less than 24 hours after this outburst was first detected, the SMC was scheduled to go into pole constraint for Swift for 10 days, and well, we were not able to observe this source for a couple of weeks after the outburst began. By the time we were able to observe the system again, it had faded completely. There was no sign of any X-ray emission from the source at all. Continued observations over the next few days continued to reveal nothing. We had to conclude that this source's outburst had completely faded within a period of about 16 days or less. This is an incredibly rapid X-ray outburst and leaves us sort of scratching our heads. What the heck produces an X-ray outburst that is this luminous, that decays so rapidly? We're again left to go to our multi-wavelength data to try and draw any conclusions we can, and the light curve, again, just sort of leaves you scratching your head. The source does not behave anywhere near in the same way that our first two outbursts did. Instead of seeing a source that's highly variable in the I band or in the UVW1 band, we see a source that's remarkably stable. We only see variations in the I band and the UV band magnitude of about 0.1 or 0.2 magnitudes for thousands of days leading up to this outburst. And however, when you zoom in on the period when we detect X-rays from this source, and these right-hand panel zooming in, you do see that there is one very interesting data point produced by the UVW1 band light curve and that I band light curve produced by Ogle. We can see that when we first detect the outburst on this first day when X-rays were visible, well, you can also see that the ultraviolet and infrared brightness of the source is increasing dramatically in this observation. We see a half magnitude jump in the I band light curve of the source over in this observation. We also see a 0.2 magnitude jump in the UVW1 band. Monitoring for the UVW1 band goes up to just 7 days before the outburst. We can constrain the duration of this an ultraviolet outburst to be less than 7 days based on S-cubed observations, because when we ran a follow-up observation the next day, well, both Ogle and Swift UVOT see the source having decayed back down to quiescence within just 24 hours before going through a period of slight dimming over the next 25 days. This is all very confusing. We have a source that's rapidly getting brighter in both the infrared and the ultraviolet. It's rapidly getting brighter in X-ray before decaying away almost immediately, leaving almost no trace that this outburst had occurred. We have one last piece of the puzzle we can try and add to this. We can produce a UV I-band color magnitude diagram. I will note that this color magnitude diagram does have the y-axis flipped from the first two, so redder is going to be producing a downward trend here. And we do see that the source does get redder over time as the source is changing in its I-band brightness, although it's not changing that much in both how red it is or in how bright the source is in the I-band, with the exception of this single point here, the point where we see the source go into its extremely bright outburst phase. So how do we interpret something like this? We're not really seeing much growth and decay in the circumstellar disk of the system, and then we see one incredibly red, incredibly bright point, and then absolutely nothing. Well, it left us scratching our heads for a couple weeks as we analyzed all this data. We had to dig into the archives of BE white dwarf observations, hoping to find something that matched what we had seen. And thankfully, there was a source that was a very close analog to what we had found. And this is a MAXI source from 2011. This is MAXI J0158-447 that first went into outburst in November of 2011. There are papers produced analyzing this by Lee et al. In 2012 and Mori et al. 2013. Now, as we can see, we again in this MAXI source have a rapidly decaying light curve in the XRT. We see that this source is only around for 14 days before fading away from view. I will note that this source also reached a super Eddington luminosity. The first MAXI detection of this source placed the maximum X-ray light curve, maximum X-ray luminosity of the source at 10 to the 39 ergs per second, even more luminous than our recent 2024 outbursting system. Additionally, if we look at the I-band light curve produced by Ogle around this time frame for this MAXI system, we see something similar happening in our 2011 source and our 2024 source. We see a very stable quiescent luminosity in the I-band before rapidly, within 24 hours, increasing in brightness, decaying halfway back to quiescence the next day, and fading away within a timescale of just 50 days. These values match up almost perfectly with what we're seeing in both Swift XRT in 2024 and for Ogle in 2024, although Maxi source does generally stay brighter instead of having a period of dimming afterwards. But we can interpret these two systems as having very similar causes for these sort of extra luminous, very rapid X-ray outbursts. And Marie does a great job of outlining the case for how something like this could occur. The suggested formation and cause of an super Eddington outburst like this is a nova on the surface of the white dwarf that is produced by a very highly massive white dwarf near the Chandrasekhar limit. In such a white dwarf, it's possible that the mass ejecta could be limited or suppressed somehow by this massive white dwarf. And if you have a very massive white dwarf producing a nova with suppressed mass ejecta, then it's possible that the thermonuclear runaway phase at the beginning of such a nova would produce this sort of brief flash of super Eddington X-ray luminous material emission before fading away rapidly. And so this is sort of the best interpretation we have of our 2024 event is that we're seeing this sort of second, very super luminous, very fast nova. This would put this, both our 2024 system and the 2011 system observed by Maxi, as two of the fastest nova to decay, as well as two of the most luminous novae ever recorded for white dwarf systems. This makes them ripe for follow-up study because this would be a very important find in the sort of history of nova observations, give us even more context for how novae behave and evolve, and suggest that maybe BE white dwarf novae are a sort of unique case where they can produce these sort of strange properties. This is the third and final outburst that we found from our S-cubed observations of BE white dwarf. So let's quickly summarize what we've learned from our three observations. We can put our properties that we found of our three sources in a table. We see two sources that produce similar, fainter X-ray luminosities with long duration outbursts. We have a mass of the white dwarf in one of the systems. We do not know the mass of the white dwarf in the second. We can interpret these two as having very similar causes. We can say that these are likely caused by stable nuclear burning, but we can say that this third source, this super luminous source that was found just last year, well, it has very different properties. It's much more luminous, it decays much more rapidly. It's likely that there's a completely different cause. We're seeing the thermonuclear runaway phase at the beginning of this massive, strange nova. This suggests that there's multiple paradigms by which these sources are going to produce X-ray outbursts. We can have these sources that sort of have growth and decay of the circumstellar disk producing outbursts. This would be the type 2 BE white dwarf analog, comparable to what we see in BE neutron star systems, where the growth of the circumstellar disk is going to produce this sort of stable nuclear burning phase where that white dwarf is going to be brightest. But as soon as that circumstellar disk radius decays back to a smaller value, well, it's going to turn off pretty much immediately, and we're going to cease stable nuclear burning, and the source is going to go back to quiescence. This is our type 2 outburst that we see. Additionally, we can see that there's the second paradigm, this BE white dwarf nova phase that can occur, where a system is going to remain remarkably stable, just sort of depositing material in the atmosphere of that white dwarf, a thin hydrogen layer at the surface of the white dwarf. When there's enough material in this layer, then, well, you're going to have the thermonuclear runaway detonate, produce this nova across the entire surface of the white dwarf. It's going to very quickly flash in the X-rays before decaying away almost immediately back to quiescence. If we look at the quiescent observations of these systems, well, these systems, as we would expect, are very, very dim, very faint emitters when they are not in a state of outburst. In fact, our 2021 outburst and our 2024 outburst have never been detected by S-cubed in the entire history of our survey outside of the two outbursts that we have detected from the sources. There have been some very faint detections of our 2020 source, this first source that we found by S-cubed, although some of them are very close to the detection threshold of Swift, so I'm not sure how many of them I believe are real. It does look like there might have been a small outburst that was produced recently that has not been followed up on yet. It's worth following this source to see if maybe there isn't some sort of quiescent emission from the system that we are missing that would sort of change the way that we view these systems. Maybe it's possible that there's some sort of added luminosity we're seeing in quiescence from some of these BE white dwarf binaries, but that is again left as an open question that follow-up observations are going to have to be performed for us to learn more about these systems. There are these Swift observations have been great. They've sort of taught us a bunch about how these BE white dwarf systems evolve during these outbursts, how they can produce BE white dwarf outbursts. But there's still a lot we don't understand about BE white dwarfs. Many open questions about the X-ray properties of these systems. In addition to the quiescent luminosity questions that we have, well, it would be great to know if these systems produce type 1 outbursts similar to BE neutron star type 1 outbursts. Is it possible that there are periods where we see brief stable nuclear burning phases similar to the type 1 outbursts we see in BE neutron stars, or are we just seeing these type 2 outbursts that are similar in BE white dwarfs and BE neutron stars? We also don't know what the recurrence rate of a luminous soft X-ray outburst is going to be in a BE white dwarf system. How frequently do these type 2 outbursts occur? For some BE neutron stars, these occur on every 10 to 15 years or so. For some of them, it's even longer. Some have only produced one X-ray outburst in the entire lifetime of X-ray astronomy of over 60 years. Additionally, we see that there's BE white dwarf novae that have been produced, but we've never detected a recurrent BE white dwarf nova system. Is it possible that there could be a BE white dwarf system that does produce recurrent novae? Is the mass transfer rate high enough that this can be detected on any sort of reasonable timescale, or is the mass transfer rate just too low? These systems should only go off very, very infrequently. We also still are not super clear on how the super Eddington luminosities of these novae are reached. There's more work that's needed. We just need to observe more of these novae to better understand what the heck is happening to produce such bright, luminous, fast X-ray novae. These sources also do reach the ultraluminous supersoft source regime, which is something that's been detected not just in the Small Magellanic Cloud, but from other galaxies. We see ultraluminous supersoft sources all over the local group. Is it possible that somehow the BE white dwarf systems that we've observed are connected to this ultraluminous supersoft source phenomenon, that there are some unconfirmed BE white dwarfs among the ultraluminous supersoft source population that we need to find some way to confirm, to connect, to resolve the BE star in these systems to confirm that there is possible that there are some BE white dwarfs out there that might be within this ultraluminous supersoft source population. And last but not least, we're seeing periods where white dwarfs undergo stable nuclear burning in these BE white dwarf systems. We're also seeing novae with limited mass ejecta. It is possible that the white dwarf in a BE white dwarf system should be expected to gain mass despite producing these soft X-ray outbursts. If that's the case, then we might want to start thinking of BE white dwarfs as candidate type 1a supernovae progenitor systems. So because these are very massive white dwarfs that are producing that are accreting material from a very high mass transfer rate companion, as well as, well, we see them gaining in mass enough to produce these sort of outburst phases. So there's a lot we still don't understand. All of these questions still have to be answered. Swift has done a great job of pursuing the answers to these questions, and will continue to pursue the answers to these questions for the lifetime of the S-Cube survey. Other missions like Einstein Probe will also play a huge role in this. We know that soft X-ray surveys are crucial for our improving our understanding of these systems, and the observation mechanisms of Einstein Probe do lend it to detecting more of these BE white dwarf outbursts, these soft X-ray outbursts in the sky. So the future is bright for the field of BE white dwarf astronomy, for the future of soft X-ray outburst studies of these systems. I'm very excited to see the progress that we've made so far and see where we can go from here. I'm going to go ahead and leave it here. I'll put my conclusions up on the screen, and I'm more than happy to take any questions that you have. Thank you so much for having me today to speak about this topic.
Right, well, thank you very much, Thomas, for a great talk on some really nice work. Kind of a virtual round of applause from everyone. I'm already seeing some comments thanking you. So yeah, let's open it up for any questions that people may have. You can raise your hand or just unmute yourself and go ahead. Yes, Sean.
Right. Get my camera in the right place. What's your take on the hypothesis that Gamma Cassiopeia stars are BE stars with a white dwarf companion that's accreting material from their disks?
I think it's very possible that BE white dwarf star or the gamma gases could be BE white dwarf stars. I think the other interpretation is they might be helium stars. The smoking gun, of course, is going to be the soft X-ray spectrum of these sources. We've never seen a gamma gas star produce one of these soft X-ray outbursts. If we were to see one of those outbursts, I think that would be sort of the best evidence we could have that to sort of support this sort of hypothesis the BE white dwarfs and gamma gases are the same objects. It might be that our the theoretical interpretation of sort of lower X-ray luminosity coming in quiescence at hard X-rays from these gamma gas objects could be the sort of same quiescent luminosity we expect to see in BE white dwarfs. It would be really nice to see a soft X-ray outburst that would sort of connect the two much more firmly than we have data for right now.
Is Tahira?
Hello, thank you for a nice talk. My question is, when you said that for PE white dwarf, we can observe them in soft X-ray, you mean that we can observe this group of white dwarf PE in soft X-ray, and but we can observe the other type of white dwarf in hard X-ray or UV? Am I
So,
right?
um, for these BE white dwarf systems, the hard X-rays, just because of the way accretion works in white dwarfs, we're just expecting them to be too faint for X-ray telescopes to detect, except when they're very close. So at the distance of the Small Magellanic Cloud, a luminosity of even 10 to the 33 ergs per second is far below the detection threshold of Swift. So it's just, they should produce hard X-rays. It's just that soft X-rays, when they're brighter, more luminous, is just going to be our best chance of finding them. So they should emit across the entire electromagnetic spectrum. It's just they're hidden behind their B star companion in the UV, and they're just very faint when they're in that accretion phase. And so at the distance of the Small Magellanic Cloud, or the Large Magellanic Cloud, we're just sort of hopelessly unable to find them right now with just how faint they are.
I'm not hearing anything. Are you still with us?
Oh, sorry, I didn't hear you. Yeah, no, I just had a question about, do you know anything about the mass of the BE stars in these binaries you talked about?
I based on the spectral types, these should be fairly massive BE stars. I think two of them have uh, uh are sort of type 3 giants, or sort of 093 giant type stars, as well as this more recent source is 09.5 V stars. So they should be fairly massive, fairly hot B stars that sort of follows the trend of these systems being sort of late type B stars or early type O stars that are fairly massive systems.
Okay, thanks. Because 20 days does seem a little bit fast. Does that all work out for the binary orbit and so forth?
I think so, but I would have to go in and do some of the math myself. I don't think it does work out for the 2024 system, I know. I don't know about for the two earlier systems. I haven't done that math myself.
Okay.
Okay, so we're just getting close to the hour, so I think we have two questions left. I have Doug and then Carol. Oh, and Dietrich. Okay, three more questions. Go ahead, Doug.
Hi, thanks. Doug Guys here. Lovely talk, Thomas. Thank you. I was struck here by the orbital periods. They seem, at least for the two systems where you got them, they were kind of short period. And I was wondering what the longest period was of the 7 so far that have been discovered. And the reason I'm asking this question is maybe this is part of the selection effect that we're not finding them, that maybe most of the systems are quite long period systems, and therefore might only have a soft X-ray transient very, very infrequently because of the great distance between the BE star and the white dwarf. Anyway, wonder your comment about that.
Yeah, I don't know off the top of my head what if there's anything longer than 20 days in these systems. I do know that in this most recent outburst, there's sort of a very a large debate about the orbital period of the system, where it was 17.55 days in the Ogle data leading up to it, but then the period shortened by almost half a day leading up to the outburst. So it's possible that the periods are actually longer and that there's some sort of like negative superhump phenomenon similar to something you'd see in cataclysmic variable stars that is sort of artificially shortening the period we see in these systems. That it's worth studying whether or not these periods are actually a little bit longer, or if there's something that, yes, that the periods would be expected in general to be longer than this, that we're just seeing the sort of strange, unique cases where we have a very short period system. So I think that it's worth looking into more and seeing if we can't constrain the orbits of these a little bit better. I know that there have been very limited observations done of these systems when they're not at outburst, and so there's a lot more follow-up to be done. I think this most recent source is the teams in South Africa, the SALT team, has been following this up more, and hopefully they can start to answer these questions.
I just want to be mindful of everyone's time. So anyone who needs to leave, please, of course, feel free to do so. Thomas, do you still have a few minutes for
Yeah,
questions?
I have a few minutes.
Oh, wonderful. Okay. So Carol, please go ahead.
Hi, it's Carol Jones. Nice talk, Thomas. I was also struck by the orbital periods and by the time of outbursts. And I noticed in the cartoons that you showed, they all looked rather coplanar. And I wondered if you consider different geometries, so that maybe the disk is at not in the same plane as the orbit of the companion, and whether that has anything to do with the outburst periods and the timing.
So the cartoons are just sort of for the simplest possible case. But yeah, I think it's sort of unknown in general how what the inclination angle is of the orbital plane with respect to the BE circumstellar disk. And I think that does play a role here in some of these outbursts where, at least in that first outburst, the best interpretation would be for the sort of multiple peak structure is that it's punching through the disk a couple different times in the orbit. And that's what's causing it to at least have those dips where we're seeing fewer X-rays. So I think it's something that we would love to pursue further. What you would need is detailed enough X-ray analysis to start to look at whether or not there's some sort of orbital period, there's some sort of a phase of the orbit where there's more X-ray luminosity being detected, which we've just never had detailed enough observations of to do. That would be your best hope of sort of maybe finding a double peak structure, which would sort of tell you a little bit more about this. You could also do it with SALT data, but this works best with high inclination systems, and that's fairly rare for these observational systems. And so that's something that, we would love to pursue more, but we just need more data to do.
Yeah. It'll be interesting too to consider any kind of precession of that tilted disk too, which is another complication. But thank you very much. And I have to run, so I apologize, but thanks again. Nice talk.
Mhm.
Okay. Dietrich?
Yeah, I enjoyed your talk. Thank you very much. Can you please remind me how you determined the periods? Did you derive them from the light curve?
Yes, so they're determined via Lomsgargle analysis of the I-band light curves, the Ogle light curves, which are very high cadence observations. Ogle observes multiple times a night for each field of view. So we do sort of see something that suggests structural changes in the light curve along the timescales that you expect in orbital period. We've never done radial velocity calculations as trying to determine the period. Just the RVs are too low at a distance of the SMC for it to be an effective way of studying the orbits in these systems.
Your interpretation is, of course, very well possible, but I would like to offer a different one. In many BE stars, we observe combination frequencies, difference frequencies between different non-radial pulsation frequencies.
Mm-hmm.
And they fall into this range, and they give you periodic outbursts in some cases. They are not easily seen by TESS because there's a calibration challenge with TESS. And so maybe you can do optical photometry and search for periods or frequencies which differ by what you think is the orbital frequency. Yeah, so I'm not saying what you concluded is wrong, but there is an alternative that is worthwhile considering.
It's definitely worth considering, and there's definitely more detailed work that could be done to sort of do that. And so I do want to sort of do more period searches within these systems to see if there aren't some combinations of frequencies that are appearing in them. So that's definitely worth pursuing as an alternate explanation that might lead to sort of longer periods for these systems.
Thank you.
Thank you.
All right. Any more questions for Thomas? Any last questions? I might use my prerogative as a host and ask you one. So I think you did a really nice job to kind of outline some of the big questions in the field and where the field might be going in the next little while. Would you mind spending like 1 minute telling us a little bit about your next steps and kind of what's concretely the work on your plate for the coming months or so?
Yeah, so I study particularly multi-wavelength variability of BE X-ray binary systems. So I'm going to be digging into the UV light curves a little bit more to see if there's any more information we can glean from Swift UVOT, which has been an untapped resource for the entire duration of the S-Cube survey. I also have been working on seeing if there aren't a few recurrent novae candidates in the Andromeda Galaxy that might have potential as BE white dwarf systems. And so I've been working with some people at Penn State to sort of dig into the question of recurrent novae and BE white dwarf systems. And so that's another step that I'm working on in the next little bit using the Hobby-Eberly telescope. So those are sort of the two areas of BE white dwarf astronomy that I'm really interested in. Again, of course, if we have another outburst, that would be huge, but it's very hard to predict when these systems are going to go off or if there's any more that will go off during the lifespan of the S-Cube survey. And so the X-ray work on the part of these systems is sort of a sit and wait patiently type of game. And so hopefully we'll find another one soon and we can do more work to examine the soft X-ray properties. But until then, ultraviolet and optical are our best friends.
Great. Yeah. So that all sounds great, and fingers crossed for another outburst, I guess.
Yeah. Yep.
But in the meantime, that sounds wonderful. Any last questions for Thomas? Otherwise, in that case, I want to thank Thomas again for presenting today. This was really great. And I'll just remind everyone that, as usual, we'll be having another seminar next month, which will be announced pretty soon. So stay posted for that. And otherwise, please have a wonderful rest of your day, and we'll see each other soon.
Thank you, guys.
Thank
Take
you.
care,
Bye.
everyone.